Hey everyone, I'm Aleksa and I am co-founder and CEO of Jarvis. And I will be talking to you about how we made our project management software run with NLP fast, and how we actually don't even need UI that much anymore since we started using NLP this way. So first of all, we've all been witnessing some of the big milestones happening, especially in the last few years in NLP. And especially since BERT came out, there has been some increased interest in conversational AI. And with this increased interest came more NLP in production. So conversation, it slowly started turning from, is this even possible, to how can we make it better and faster and actually run in production? So with Jarvis, we've encountered many problems related to, especially to inference speed. So we had to solve them fast just so we can get them to our users. And first, I will talk a bit about what is Jarvis and why the speed is this important to us. So Jarvis automates repetitive parts of project management using natural language processing and makes getting information in and out of the software available with a single sentence. And since there is a gap between what employees want, and that is the focus on their work, and what managers want to have as much information to draw conclusions from, this gap becomes even wider and wider with remote and asynchronous work. So as we can see on these graphs, what we do is try to take away all the communication between managers and employees themselves, and go through Jarvis all of this communication and data processing so that we can just work remotely and asynchronous. And we do this with a system of smart notifications from which you can update work through either text or voice and receive status updates without even slightest need to go to UI and fill out forms. So we analyze all this information and present it to managers in a way that they can find useful and draw conclusions from. And when you compare this to the current process, which requires you to manually search, enter, and submit everything, this requires managers to either make sure everybody did this or they had to work with incomplete data. We can notice like how much time can be saved. But to do this, we have to have our conversational AI actually work in real time. And for this, and not only real time, but of course be accurate. And for this to be possible, we need both accuracy and speed to be going for us. So if I'm to be honest, our first version of Jarvis, we were first of all researchers, and then I guess gotten more into the development. So we started thinking like researchers, and let's see what's the best accuracy we can get. So we started just badly when it comes to productionizing that model that we were making, and we bought into the hype and thought we could do everything with a large do-it-all transformer with some like additional layers, like fine-tuning and everything. And we've written all the code sequentially, especially like the pre and post-processing code. So we didn't really care about anything away from that model. So we were just being like, okay, we will build one big model with all the data that we have gathered crammed up into it. And this will give us great result because all of this data is connected and all of these tasks are connected. And we did get good accuracy, but our whole process from users sending the message to them receiving the response, it took around 10 seconds. And that's only for one conversation. If there are like concurrent conversations going on, this request takes even longer and performance just started rapidly going down. So we knew we had to improve this and that we couldn't do like full production with this type of model. And I mean, first thing that comes to our mind in this case is just, we were testing this out on CPU. Let's see how it works on GPU and see if this is a good enough option. And it did improve, but not nearly enough for this option to be viable, because it would be a lot expensive since we would still have to have a lot of GPUs for a lot of concurrent conversations. And we also like tried to code things a little differently, like vectorizing the code wherever we can, list comprehensions, generators, just trying to follow, I guess, good practices when it comes to running the Python code faster. But the thing is that we were using too much data science where we didn't have to, and especially machine learning. And we weren't specializing parts of our system enough. We wanted to do everything sequentially, going to our big model that works so great. And I mean, everybody gets excited when they get this one big model that can do so many things. But we knew we couldn't get this to users and get them to use it this way. So we had to stay back and think, how can we redesign the system to work better for us? And the little things that we didn't care about during the research really started to matter when it comes to using this model in production. So wherever it didn't hurt the accuracy, what we started doing is breaking down the models into like atomic inference. So what I mean by that is we actually wanted one model to do its specific thing. And like the lowest possible specific thing. Like if we can boil it down to simple classification, that's what we are just going with. And we a bit stepped away from deep learning for some of the models. Some of them, of course, still have to use it, especially like those BERT-based models. And even like in some parts, we even like totally stood away from machine learning, data science, and some we just did like statistical models, let's say. And what it turns out is not that it only made it faster, but it also made it a bit more accurate when we use statistical models where we can. So, but I mean, of course, when there is context involved and everything, we can't. But for example, if we have to match like closest name to the one that was misspelled, statistical models will still better than that. And like, unless we want to do like complete, like for English names, we can do that. But for some names that aren't that common in data sets, we had to do some statistical models. And the second thing we did is just what I mentioned. So moved away from deep learning when needed and when possible. We also started harnessing power of concurrency. And this is where a lot of time has to be spent just thinking which parts can actually be done concurrently, because some parts do have like some sort of relationship where you have to do them sequentially, but it's actually much more common that you can do concurrent things that just speed up things a lot. And in our case, we also moved away from Python to Go for non-machine learning stuff. Or of course, for machine learning, we still kept Python. And this improves our speed incredibly because it harnessed innate concurrency that Go has. But I mean, if somebody is more comfortable with Python, there are also like Cython and some other solutions, Spacey, that speed up execution in Python without having to like change the language. So with all this in place, we had already improved our model considerably, but as number of concurrent requests grew, we wanted to do something more just in case, so that we wouldn't fall again into the same thing that we had before, where we thought we were good enough, but then it turns out when the number of requests increases, we're not. So what we wanted to just check out, how can we actually build this inference to be better? So until now, we have building everything around the models themselves to be better and like breaking them down and everything. But we wanted to see if we can also make those models work faster and infer everything that we've trained them faster. And some of the things that we tried next, first, we started using TVM on AWS. And this helped model inference speed, but we wanted to see if we can push it further. So we tried Onyx runtime, which turned out to have like massive impact on us. And for those who might not be familiar with this, Onyx is a format representing ML models, and the Onyx runtime is a high performance engine for running these models. And it's sped like our inference drastically, so much so that right now, for each of our models, it's around 10 milliseconds inference. And for some of them, it's in like single digits for some of the simpler models. And this makes the whole conversation look completely real time. Like even if we have a lot of pre-processing and post-processing after that inference, it still helps a lot to make it like completely real time. And another thing that we would like to try soon as we start implementing, especially like document summarization, question answering, and some more complex feature, is TensorRT to see if this can speed us up even more. And if someone has good insight on how this works with transformers models, please do tell us, so we would know if we can, if we should pursue it further. And yeah, thank you for attention. And if you would like to hear more about Jarvis or chat about machine learning and conversational AI in general, you can reach out either by email or my Twitter, both are stated here. And yeah, now I guess we're moving to QA.
Yeah, great. Thanks a lot for the talk, Aleksa. And yeah, I encourage folks who are in the Zoom or on the YouTube in the YouTube chat to post their questions as we're going. I've got lots of questions. I'm very excited to ask them. So the first thing I'd like to ask is sort of towards the end there, more of a detail-oriented question. But why did you choose the ONNX format? Like what made you look into that originally? And also what do you think is the secret behind why it was able to give you that big performance boost?
Yeah, so it wasn't like the format itself, but like it's actually the ONNX runtime, which Microsoft developed, and they especially updated it like a year ago, I think, for BERT, which we are using underneath. So they even like, I mean, this was in research settings, in like their lab settings, but they got like nearly 20 times improvement on both CPU and GPU. So that got us going. We didn't get, let's say, that much, but we still got like 5 to 10 times X, which is pretty good. And we're right now able to even run it on CPU. Like we don't need any GPUs for the inference.
Mm-hmm. I see. Yeah, because I guess, so I have come across the ONNX format only as just sort of this attempt to get everybody to play nicely with each other by sort of some of the people coming into the field later, right? You've got TensorFlow and PyTorch both have their solutions, and it seems like a lot of other people have been like, okay, can we agree on an open format? So it's actually, this is great news to me to hear that the open format can also bring you these performance benefits.
Yeah. So I mean, Microsoft is the one pushing that format, especially. So that's probably why they created this runtime. But when we like researched a bit deeper, this runtime really helps.
Great. That's cool. That's a nice detail about operating these things that I was not aware of. You mentioned being able to deploy just to CPU being important. Is that mostly just to reduce cloud costs, or is this something that you can see maybe running on unspecialized hardware in phones or something like that?
Yeah, so we right now are doing this on AWS, and we're just trying to reduce the cost as much as possible. And I mean, we didn't even need that last steps that I like put the last slide. We still have it like real time even without that. So when we implemented this made it like, it gave us a lot of space to just go completely away from GPU for now, at least. But yeah, at some point it would be great to just be able to also do it on the phone directly, so that you don't have to actually have an internet connection to, like, I mean, if you're on the airplane and you can't do, you just remember something so that you can do it right away, and then it gets uploaded when you get connected to the Wi-Fi. So that is something that we are looking into.
I see. Yeah, you also mentioned the sort of one of the pieces of the transition from your original application to the second application, the like more performant one, was you moved from one like single almighty transformer model to many small models. So this is something that it seems to have been coming up like quite a bit in a lot of the conversations I've been having with folks on the salon, that people are moving over to these multi-model model amalgamation type pipelines. So I was just wondering if you could comment a little bit more about that process, what worked well, what didn't, what were the pain points, and the tools that you used to switch over your pipeline, because it's quite a different thing to manage a zoo of models than a single one.
Yeah. So at first, let's say we saw that a lot of people in the beginning, since we started working on this in the early 2019. So a lot of people at that time were just taking it straight away. It was probably hype, but everybody was like, yeah, this is a silver bullet. So we were like kind of onto that hype. And then we saw that, I think Sonos acquired the company for like 50 million. They'd used especially like just one model, And like they used one joint model for like a bunch of NLP tasks. And we were like, if they can build it that good to be actually acquired, I mean, there must be something there. So we started just going straight to the joint model that does like a bunch of other tasks. But like as we went going on about it, we noticed that a lot of those things can be done concurrently. So instead of actually just going everything sequentially to that one model, we started building a lot of models that can be done in different like timestamps. And we did I guess we did have to work a bit more on the architecture, since we have gRPC communicating between those microservices and everything. So we did have to do a bit more architecture designing in it and just implementation details. But it helped us even with all the networking costs between those models. It still helped us a lot with the speed.
I see. That is, I guess, the biggest thing I see as somebody who's more of a like machine learning researcher than a machine learning engineer or an ML ops person. That seems like a pretty big hurdle to come over, this like ops problem of integrating that whole pipeline.
So it seemed at first, actually, but it's not. Like once you build a communication between two services, the rest become like incrementally simpler. So there's a lot of code that you can basically just copy out. That's like for the communication, and we completely removed states from most of these things. So we didn't actually have to save states at any point. It was just basically kicking the states around. So a bunch of codes was similar, just receiving the state, then packing it up for the next thing. So it even though it seems like at first as a big hurdle to overcome, it's actually not. We did it like in less than a month, just switching to
that. So that's kind of related to another broader question that I wanted to ask. You mentioned that early on you were effectively doing like too much data science, too much machine learning, right? So how do we take some of these, and you eventually learned the lesson to kind of pare that back, right? So how do we take like that lesson and the lesson of like, it's a good idea to have multiple smaller services communicating with each other and sort of incorporate them maybe earlier in our workflow? Because when I talk to people, it seems like they all, like a lot of them have that same trajectory of paring things away and adding more like of a complicated ML ops structure. So what do you think we can do to get those earlier in our development cycle?
Yeah, so I mean, for us, it was just, I guess, trying it out and seeing what works, what doesn't, and probably like everything won't work the same for everybody, but just trying to think, what can you break down as for the like multiple, like which parts can you break down into simpler problems? Like you don't have to have a silver bullet, and you usually can't have a silver bullet for everything. So just trying to think what can you and how can you break down this problem into much more like smaller problems, and then also, are those smaller problems actually best solved this way? So don't think like just try not to go with the feeling, let's say, but actually the reasonable explanation. So we were like, yeah, machine learning is totally going to kill it here, but it turns out that it doesn't. And like statistical models are much better matching like misspelled names than any deep learning or even like basic machine learning model. So just
a quick clarification. When you say statistical models, are you talking about things like, I don't know, like hidden Markov models for language, or do you just mean like like probability, like forming a probability distribution over tokens? Like, what are you talking about here?
Yeah, like what we used was Jarrow-Winkler. So like, or like Levenstein's distance. So something that's that's not really it's not even, I guess, a complete model. It's just computing what's the closest to something else in some sort of way.
I see. Yeah. So often people say that ML can replace the need for hand-engineered features, right? So like the SIFT features or Laplacian pyramids for images. I know a little bit more about images than I do about NLP. So those are the examples that immediately come to mind. Like those have been effectively replaced in a lot of models by like the first couple layers of a ConvNet, essentially. But that doesn't mean that there aren't tons of places where actually doing something like that, and pulling out those nice features can get you really good performance on one part of what your model needs to do.
Yeah, exactly. And I actually started as a computer like vision engineer as
Mm-hmm.
well. So when it comes to that part, even though for hand gestures, we did use uh, deep learning. So, but like for some kind of to actually detect some things like movement or something like that, we used a bit simpler models. So, I mean, it was like 5 years ago, so I'm not that like great remembering exact details, but I actually do have like a patent for a shelf during that time. But yeah, I'm much more into natural language processing right now.
Yeah, so I guess I did want to get a little bit of your opinions on what's going on in natural processing these days, natural language processing these days. So the zeitgeist now seems to be like transformers. Transformers are it. We just need to get like the attention mechanism. We need to find a way to make that efficient. Then we need to scale that up, work with internet scale data, like GPT-3 is the move. Now we just need to make it smaller. Do you think this is a good direction for the NLP community to move in? Do you think this is the right one?
So I think it depends on what actually you want NLP to do. So if you need NLP to just analyze the text, extract some information from it, and like just that sort of things, that the transformer can be really great. But just like you said, like getting more data, making it more sophisticated and everything. But I don't think it's a solution to a broader problem of language. So I don't think that actually it can solve communication that isn't, let's say, even like you don't know what's going to happen. It's not really predefined, but it's not like an actual conversation going on, since like it can just spew out anything that it read from the internet, which can be good, bad, terrible. It is, so whatever is the most common connection with something else. So it's not like, it's not reason communication per se.
I see. So do you think that is something, some of that comes from the choice of using the cross entropy loss, this sort of like contrastive learning thing where you're trying to say, okay, like predict this next token by using all these negative examples of like, it's not, masking things, all these kinds of approaches. So do you think that's an architectural limitation, or do you think that's a problem specification limitation there?
So for me, I think it's actually like the problem specification, since it's completely different to have some sort of um, real reasoning, to get to real reasoning from that. What you can do is analyze a lot of things that humans already, like you can use tools that humans already use to pack it up and get something new there, but you can't actually uh, at least for me, can't build totally out of the box. Like it can be something that satisfies the closest possible thing you want to get to, but nothing like so I'm not sure like how to explain where I'm going at, but like in manufacturing, you see like those shapes that get really good results and everything, but they're just trying to satisfy a goal that was given to them. But they can like really think out of the box and be like, maybe we don't actually need this thing at all. Maybe we can build something completely different. Like that is lacking for me.
I see. Yeah. So this, yeah, related to the sort of problem of, out of distribution generalization, sort of rule extraction, things that people are finding computer vision models approaching, like the problem of self-driving, have also run into like that kind of difficulty or issue. Yeah.
Pretty much. I haven't like been researching that much self-driving per se. Like, I mean, I think self-driving can work great if a lot of self-driving cars are out there and they communicate between themselves and everything is great. But I haven't researched enough to talk about like a real world scenario where there's like a bunch of random things going on. But in natural language and or like in manufacturing, like I said, it can like build the best goal, like build the best box for this, but it can say you might not need this box at all. Like just put this box away and do something else. That's something that I don't think is still available.
Yeah, that makes sense. At least, for in the early days of computer chess, I don't know if this remains true, but some of the even after computers beat humans, the best solution was a sort of like human-computer hybrid, not in the Deus Ex, or cyborg sense, but in the like just two people, like or a computer and a person working together. And so it seems like that's kind of the sort of thing that you're going with Jarvis, in that there's a step of automation of information extraction and collection, but the whole process is not being automated, right? The whole process of managing employees, of managing a project, is not automated. It's an adjunct, it's a tool that aids somebody who is, an individual human making those kinds of decisions and capable of that kind of reasoning.
Yeah, exactly. It's about improving like performance of those people so they can focus on something more important. And like some different example is just in medical field. Uh,
Mm-hmm.
there are some like medical images that machine learning models can just find some things that doctors can't. But then on the other way, there is something that only doctors can see. So it can work like best if it's a hybrid thing.
Yeah. Well, I think actually I have one more question for you, which is so you're in. Have you been using weights and biases as part of your natural language processing model building toolkit? And if so, like what have you found? What have you found useful? What have you been using?
Yeah, so I have been using it, and I started actually using it a while ago when we started using that one big model, and it
Mm-hmm.
started it started at first because it took a lot of time to train that big model, and then you had to do like a bunch of different tuning parameters, like either write code yourself. So back then, I think it was like mostly just that thing that helped the most. So that's how I started using it, and I still find just sweeps. They're really best thing about it because it just goes through every single possibility and logs everything that's happening during that process, and
Mm-hmm.
especially like utilization of CPU, GPU, and stuff like that was helpful for us because we can see if like during that case would we need like some sort of change in the future.
Mm-hmm. Great. Yeah, I'm glad to hear that the tool was useful. I think the artifacts toolkit is maybe newer than when you were working on that particular part of the project. It might be helpful for orchestrating that model pipeline where, or the end where you have things that are not just deep learning models that you want to, combine together and communicate with one another. Um, but yeah, well, thanks so much, Aleksa, for staying up late over there in Serbia to be able to come on and talk with folks and answer questions live. And it's a really cool and exciting tool, and I look forward to seeing, how you guys grow and make great use of it.
Yeah, thank you so much for having me. This was really fun, and it was also fun to hear from Richard what he's doing, and like I mean, just that sort of uh, kind of competition, but it's also like you earn even if you don't like completely win. It's really interesting thing to hear.
Mm-hmm. Yeah, well, thanks for coming, Aleksa, and thanks to our audience on Zoom and on YouTube for coming by. I hope to see you all again in 2 weeks when I'll be giving a talk, and Chirag Agarwal of Harvard will be here to talk about his variance of gradient paper. So I will see you all then. Take care. Bye.